In this video, we are going to look at the chemical reaction lab. The first type of experiment is a single displacement reaction. We'll show you the experiment and then we'll go back to a little visual of that. I'm going to grab a clear solution of 6 molarity hydrochloric acid, put about 20 drops in here. I'm more of an estimate. I'm okay with that. And this is a clear solution right here. And then I will grab a piece of zinc metal. I will drop this metal into the hydrochloric acid. And I think you should probably see some pretty good bubbling coming up right away. So there's bubbling coming up. Okay, if I feel down here, this is getting pretty warm. Okay, this reaction as well. So I got this reaction going. I'm getting some bubbling. And as that bubbles, I'm going to light a wood splint. And we'll see if I can do this with my left hand. I'll light a wood splint here. Get that wood splint going. I'm going to get rid of this. I'm going to take this wood splint and put it underneath the hydrogen, and we get a pop. And that popping sound actually indicates the presence of hydrogen right there. So that is our first reaction. Let's take a look at it in paper. So I'm going to bear with me as I go to a screen share here. And we'll find it, open it up. And here we go, chemical reaction lab. Just going to grab a little annotation piece and a little note here thing. And we're going to write the word equation, then follow it with the balanced chemical equation, including something called subscripts. And then we're going to answer any questions. We're going to do that with the different reactions for this lab, and there are 6 of them. So the first one is our single displacement reaction. All right, and I took zinc plus hydrochloric acid, which has the formula hydrogen chloride, and that produced hydrogen gas and zinc chloride. So essentially, the positive ion here of hydrogen was replaced by the positive ion of zinc, leaving hydrogen by itself, and then the zinc goes with the chloride. So one thing was being replaced, which was the hydrogen by the zinc. This would be a single replacement or single displacement reaction. That's the equivalent. All right, zinc is not part of Brinkelhoff, so that's the end, and it was a solid. Hydrochloric acid is H+1, Cl-1. It was dissolved. Those ions are dissolved in water, so it's aqueous. And let's see, hydrogen is part of Brinkelhoff. That travels in pairs, and that was the gas. And we just proved that gas by actually sparking it with the flame and then having it pop. And then the last thing in the solution remaining, okay, what's left of that is zinc chloride. Zinc is +2, Cl is -1. So this is a balanced chemical formula. So first off, I get the balanced chemical formula for each thing, but then I go back and balance the equation. I have a zinc on the left, a zinc on the right, an H on the left, 2 H's on the right. So what that means, I'll have to put a coefficient out in front, and I'll put a 2 out in front here. And when I do that, that means I have 2 Cl's, but I have 2 Cl's here. So this should be balanced, a 1 to 2 to 1 to 1 ratio. And this would be the chemical reaction right here. Okay, the other part of this is looking at the bullet points here and learning about the different reactions that we have. Just gonna go back and spotlight. And we have an activity series. And this is an activity series for metals. Is the list of metals in order of reactivity, with the most reactive on top and the least reactive toward the bottom. Now, there are other metals that fit in, but I took this one out of your book and I just took the selected ones that are here. Let's see. So in other words, if we took zinc and combined it with hydrochloric acid, which is a hydrogen, zinc will replace the hydrogen, okay, without any extra. Automatically on its own, it doesn't need any extra energy to do that. In fact, it releases energy. If I put copper in hydrochloric acid, nothing would happen. Okay, if I put silver in hydrochloric acid, nothing would happen. But any of these metals above hydrochloric acid would react with that in the reaction. A couple examples that we had were in lab, I think we had iron replace copper in copper chloride. And then we took copper and had it replace silver in silver nitrate. So iron replaced copper because it was above it. Copper replaced silver because it was above it. Okay, and in this case, zinc replaced hydrogen because it was above it. So which one's most reactive? The one that's highest up, zinc or hydrogen or copper. It would be the zinc because it's highest in the reactivity series. Right, that is reaction one. Let's take a look at reaction number two. And this is a double displacement reaction. And just do a quick erase here and get this number out. Okay, and let's go back here. And we have lead nitrate plus sodium iodide. The lead positive ion will combine with the negative iodide, and the positive sodium will combine with the negative nitrate. So you get lead 2 nitrate plus sodium, lead 2 iodide plus sodium nitrate. I write the balanced chemical formula. Lead is +2, NO3 is -1, so I need to balance that with a 2. Na is +1, I is -1, so that's balanced. Notice I got TB is +2, I is -1, so I put a 2 there. I have to adjust the number of I's based on the lead, and Na is +1, NO3 is -1, so that's balanced. Okay, so balance your chemical formulas first, then go back and I'll just do that, balance the equation. So you have a lead, you have 2 groups of NO3, so I'm going to put a 2 in front here. That gives me 2 NO3s, but it also gives me 2 NAs, so I'm going to put a 2 in front here. And that gives me 2 I's, and I have 2 I's, so that'll be balanced. Now there's some questions about conservation of mass and some other things that we're going to look at and then and do this reaction. All right, so I think what we'll do is do the reaction, then we'll show you those different pieces from right there. Let's do a quick erase here and get those out of there, but we know it's a balanced equation. And then I'm going to go to a screen share here. I'm going to stop my screen share and get to where you can actually see this reaction. Okay. And I have this reaction. I don't know if you can see this here. I have a solution right here. And there are 2 clear solutions. There's a test tube with some lead nitrate, and there's a clear solution of sodium iodide on the bottom. What I'm going to do is I have a balance over here, and I don't think you're going to be able to see that, but I'm going to weigh this, and it weighs 97.93 grams. Okay, and then what I'm going to do is I'm going to take this and invert it and turn it upside down. Turns yellow, and that yellow is chunky, which means there's a precipitate or a solid that formed. I don't know if you can see that from there, but I'm going to weigh it again. And 97.93, I think it looks like it is the same as before. Both times it was hovering between 97.93 and 97.94, just because of air in the room, not because of an error with what we call conservation of mass. So let's go back to our questions on the screen share and just take a quick look at that. All right, so coming back here, we had our balanced equation, and let's see, bring this back here. And I suppose I should put these numbers in. And then we know that's a 2 there and a 2 there. Didn't really keep those in there. But what is the conservation of mass? That is the mass of the reactants equals the mass of the products. So mass of reactants equals the mass of the products. And we know that's true about every chemical reaction because the number of lead atoms on the reactant side and the number of lead on the product side are the same, or the number of sodiums on the reactant side is the same as the number of sodiums on the product side, and so on. Okay, let's keep going and look at a couple of these other questions. How does this reaction show the conservation of mass? We demonstrate it because we did the reaction in a closed vessel like this, and the reactants and products weighed the same after each time. So that was kind of our verification of conservation of mass through an experiment. Define precipitate. Precipitate is a solid form when you combine 2 solutions. So I started with 2 aqueous clear solutions, one in the test tube and one in the bottom of the flask. like this, something like this. Okay, there's a test tube and both were clear. Okay, and then I got a solid. I don't know if you can see the bright yellow, but if you look closely or we're here, you could actually see chunks forming, and those chunks of solid would be precipitate. And then lastly, we have which product is a precipitate. Hint, all nitrates are soluble. If we go back here and look, we started out with two aqueous solutions. If all nitrates are soluble, then that couldn't be the precipitate. It has to be the lead iodide, and that's why I put a solid there. Lead-based paints were used for a long time because they get brilliant colors. I mean, this is a brilliant yellow, a lot of appeal in using it, but I'm led to believe the toxicity has become a problem with wider spread use of that. All right, that's reactions 1 and 2. We'll have another video with reactions 3 and 4. Thanks for watching.